This is Module 3, Energy Systems and Exercise. Here we are for Sports Nutrition. Dr. Jenkins in the house. This one might be a little intimidating, but I'm really happy that you're listening. So for those of you that are listening, I think you're already a step ahead of the game. Some of these things are a little complicated, but not with me helping you through it. So we're just going to try and hit on the most important things. All right, so we talked in the last chapter about fuel sources, okay? But now we're going to be a little bit more specific. How does our body use those fuel sources during what kind of exercises, when, in what order? How does that get to the muscle? We're going to get a little bit more down to the muscle level. But don't be shy. I am here to help you. Hey, there I am, leading the Peloton. Yeah. With a bunch of like middle-aged white men. But hey, still, listen, I was still leading the Peloton at least once. Okay. We're going to start with some muscle structure. This isn't specifically in the Jake and Droop text, but I think it's really important to have a basic understanding, so I'm adding it here. Any question I ask you on a quiz or a midterm or a final will be included in this PowerPoint. All right, so when it comes to muscle, it turns out in our body, there's actually 3 different types of muscle. What you think of, we're going to now be a little more specific and call it skeletal. Your biceps brachii, your quads, your hamstrings, these are the muscles that are attached to bone. This is what you think of, really. And did you know we have over 600 skeletal muscles? That's pretty crazy. The number gets so high because of all the tiny little muscles in our hands and our feet, in our face that move our eyes and our mouth, all that. But over 600. I'm not going to ask you that 600 number. I'm just saying there's a lot. So we're going to be focusing on skeletal muscle because that's the muscle that moves our joints, and that's what we think of. However, I am just pointing out that we do have other types of muscle tissue in our body. We have smooth muscle, which lines our digestive organs. And we have cardiac muscle, which of course makes up the wall of our heart. Those are also very important, but our focus is going to be on the skeletal muscles. Okay, if you take a sample of muscle tissue and you put it under a microscope after you've added some dye for contrast, this is what you will see. Kind of a cool picture, huh? It's considered to be striated because it has those vertical kind of white little stripes. I'm not going to ask you that, but I would like you to know skeletal muscle is voluntarily controlled. You decide when to contract your biceps brachii. You decide when to contract your calf muscle or gastrocnemius. This is different from the cardiac and smooth muscles, which are controlled involuntarily. Okay. Also, what is unique about skeletal muscle, it is quick to contract. Out of all the muscle types, skeletal, smooth, cardiac, skeletal contracts the most quickly. It contracts with high force, right? The most force out of all the muscle types, but it tires easily. I mean, you can't have it both worlds. You can't have a muscle tissue that contracts with really high intensity that can stay at that high intensity for 3 hours. It just doesn't work that way. We have skeletal muscle tissue in comparison to smooth and cardiac, contracts with more force, but can't stay contracted quite as long. On the other hand, cardiac muscle, while it's very forceful in terms of pumping blood out, comparatively, cardiac muscle doesn't produce as much force, but it can stay contracted all day, every day while you're alive. When you break down skeletal muscle, so here was a look under a microscope. If we just take a look at the muscle itself, here's the muscle belly. I mean, this could be your biceps brachii. Well, when you start to look at it a little bit in greater detail, you see that that entire muscle is made up of little segments. Let me use the yellow. Made up of little segments. And each of those segments is made up of tinier segments. And each of those tinier segments is made up of even smaller ones and even smaller ones. So it kind of looks like a fiber optic cable or electrical cord where there's an outer wrapping over many, many, many smaller little pieces. I'd like you to know some of these. And again, I apologize. Some of these blocks were meant to be like a bracket, right? So we have the whole muscle. I'm talking about skeletal muscle. It has these little chunks. But what I want to start with, and each of those chunks comes out into this little chunk. What I want to start with is this piece right here. This is what's called a muscle fiber. We're going to spend a lot of time talking about muscle fibers. Some are fast twitch, some are slow twitch, yada, yada, yada. It's just a smaller unit of a skeletal muscle. If we continue to break down that muscle fiber into smaller pieces, and yet smaller pieces, we will get to the smallest individual pieces of muscle, known as the myofilaments. These are the only two pieces I'd like you to know: the muscle fibers, small units of a muscle, and then within that muscle fiber, there's even the smallest, tiniest little units called myofilaments. You may have heard of these before. What we're going to find out in a minute is this yellow and purple one is the actin myofilament. The red one is called myosin. But they're the smallest ones, and these are the contractile proteins, what actually slide past each other to cause contraction and movement. Here's a real life picture. So here we have, let me use black. Here we have the whole darn thing, whole muscle. It has these smaller, let me go to blue. Sorry if I keep moving around here. Then we have these smaller groupings. And each smaller grouping has yet another smaller piece. And we could even go more microscopic than that. Pretty cool. Okay. So now that we know that there's skeletal muscles and that they have these smaller and smaller pieces that make them up, let's get into more detail. I'm going to use the analogy of different types of cars. The Bugatti Veyron. Oof. Yeah. I don't think anybody I know is driving one of those. Easily over a couple $100,000. This is a sports car. And then we have the everyday car. Well, our muscles are tuned differently. While our skeletal muscles have the same, for the most part, structural parts, like a car engine. Every car engine has to have the engine block, the radiator, the pistons. Our skeletal muscles have to have the muscle fibers, the myofilaments, actin and myosin, but they're quote-unquote tuned differently. Okay? And this is how we talk about muscles and energy systems. I'm going to give an example, like a quadricep muscle. Right? Quadriceps muscle. Your quadriceps muscles are very powerful, quick acting. These are the sexy muscles. You want to show off how much you can do a leg press. That's cool, right? So this would be analogous to our sports car. So some of our skeletal muscles contract really high intensity, but cannot contract for long periods of time. Your quads are meant to contract really forcefully and then take a rest. So it's kind of like that sports car. We want to be able to zoom down that dragway, zoom, really high intensity, but it's not very good for long road trips. That's when you take the Toyota Corolla. So our postural muscles are tuned and utilize energy systems in such a way that it's an overall weaker contraction. I mean, which muscle can contract with more intensity? The quads or your abdominal muscles? Well, your quads can contract with more intensity, just like the Bugatti Veyron can drive faster. But this is not going to be able to stay contracted as long. The abdominal muscles are meant to contract at a so-so intensity, kind of like the Toyota Corolla can go at a so-so speed, but it can stay contracted for a longer period of time. So it contracts at slightly lower intensities, but it can stay contracted for longer. And these are your posture muscles. We have to contract our abdominal muscles very often throughout the day just to hold our body up. So our muscles are tuned differently, and that shows in how we're going to utilize fuel. Your quadriceps, your really powerful, high intensity but short duration sports car muscles are going to pretty much rely on carbs. When we get to the postural muscles that can't contract at as high of an intensity but can stay contracted for longer, they're going to utilize more of a carb-fat mixture. So they're tuned a little bit differently. They use a little bit different fuel combination. Just trying to make a point here. Okay, one example of this fine tuning would be two different types of muscle fibers. We've already established that we have these smaller units. We have these smaller units in the muscle called muscle fibers. Well, even though they're similar in structure in most muscles, there are two types. Hey, there I am again. Ironman 2021, baby. 112-mile ride before a marathon. No biggie. So we have what's called a type 1 muscle fiber. And a type 1 muscle fiber is more of your endurance fiber. Cycling is usually an endurance event, especially in the Ironman. So it takes longer to contract. It requires more oxygen. It is a weaker contraction, but it lasts a long time. Kind of like the abdominal muscles, like the Corolla. Versus, that's a type 1 or slow twitch, type 1 muscle fiber, or a type 2 muscle fiber, which is more for quick, high-intensity activities. Usain Bolt running 100 meters. A weightlifter, intensity. Contracting with so much force. So it contracts quicker, stronger contraction, but only short-lasting. And this requires less oxygen. So here's an example of some of that fine-tuning. If we are asking our muscles to do something more of an endurance, it's not as high of an intensity, but we want to hold it for longer, we're going to be contracting or utilizing more of our type 1 muscle fibers. If you want to do more high intensity, we're going to be utilizing more of our type 2 muscle fibers. Now, we tend to, let's face it, every muscle has a combination of both. So it's not like your quadriceps have only type 2. No, it's just that your quadriceps may have more type 1 than type 2 muscle fibers. So we have a combination of both. But certainly in certain muscles, we would expect to see more type 1 or type 2, depending on what they're being asked to do. We can look at this under a microscope. We can take a muscle sample, we can stain it, and then you can see that the different muscle fibers stain differently. Type 1 muscle fibers are the lighter brown. Type 2 muscle fibers are the darker brown. So on the left, this might be more of a postural muscle or an endurance muscle, more type 1 muscle fibers, whereas on the right here would be more of a quick, high-intensity muscle, like your quads. So every muscle is a combination of both type 1 and type 2 muscle fibers, but there'll be different concentrations. Okay, Another picture of me, blah, blah, blah. Okay, so we already identified muscle fibers. Oh, that's the wrong part. Sorry. Muscle fibers are here. Boop. We've identified muscle fibers. There's type 1 and type 2, right? Endurance and high intensity, short lasting. Now let's talk about those smallest pieces called the myofilaments, actin and myosin. These are the parts of the muscle that slide past each other to cause contraction. You should know, actin is the thinner one, myosin is the thicker one. Pretty simple. Actin is thin, myosin is thick. Now, I know it can be a little confusing because we're seeing this picture, how we go from big to small for a muscle. Well, if you were to slice, muscle tissue a different way, we would be able to see that the actin and myosin kind of line up in horizontal lines where we have, let's say, the blue is the actin, and then the myosin kind of looks like this. Okay, it just means that the actin and myosin, they kind of align themselves horizontally. And when a muscle contracts, the actin and myosin slide together. So when a skeletal muscle contracts, it's called the sliding filament theory. All I want you to know is that when a skeletal muscle contracts, the actin and myosin slide past one another. Excuse me. So initially, there will be a little space in between them. So this would be muscle that is relaxed. You see this little space between the blue lines? Space. When a muscle contracts, there's no longer space between them because literally the actin and myosin have slid together horizontally. Now, if you wanted to take it more specifically, you could. There's first cross-bridging, where the myosin head reaches up and attaches to actin, and then it is the power stroke, where the myosin head releases stored energy, and the actin and myosin slide together. But you don't need to know those specifically. Just need to know the basics. The sliding filament theory, how a muscle contracts, skeletal muscle, actin and myosin, which are arranged horizontally, slide past each other. Right? So here's a relaxed muscle where there is space here. And then a contracted muscle when that space is no longer there because actin and myosin slid together. Pardon me, it's allergy season, I guess, already. All right, I hope this animation still works. You could certainly go to YouTube and find many animations on the sliding filament theory. You don't need to know specifics above what we talked about. It's just there if you like. Pardon me, I'm sorry. Okay, so now that we know that when a muscle contracts, the myofilaments must slide together. Well, in order for the myofilaments to slide together, they need a fuel source. So the process that we just talked about requires fuel. I mean, the actin and myosin aren't going to move on their own without any fuel. If you ask that Bugatti Veyron or Toyota Corolla, it's not going to go without fuel. So we got to have some kind of fuel. And of course, nutrients are that fuel, carbohydrates and fat. So how does it work? This is really simple. I know it's a lot of words, but it's really simple. We eat. Gobble, gobble, gobble. Break down the food, absorb them. Those nutrients go to the muscle cells. The nutrients from that sandwich you just ate will eventually make their way into the bloodstream, which will eventually make their way to all the skeletal muscle cells. And something that's important is that we have to convert those nutrients. We have to convert those nutrients that we just brought in into a usable energy source called ATP, adenosine triphosphate. But what's unique about this is that even though we can burn glucose, carbs, we can burn fat for energy, that fuel itself is not in a usable form. So we have to convert everything into this other fuel that's usable called ATP. ATP is what is the energy force that gets actin and myosin to slide past one another. So, okay, same slide. How do we do it? How do we get those nutrients, carbs and fat, into ATP? That's the name of the game, folks. We bring in the food, we digest it, absorb it in the bloodstream. Carbs and fat go to the muscles, but they've got to convert it into ATP because that is the usable energy, because the ATP will cause actin and myosin to slide past each other. Okay. You don't need to know the specific word, adenosine triphosphate. We will be okay just using ATP. Remember, ATP is the usable energy source. The ingested nutrients like carbs and fat cannot be directly used for fuel. We always have to convert them into ATP. Okay. Now, we're going to get into a little chemistry. I'm sorry. We have to. So, let's just review. And I apologize for going over it and over again. My goal is just to really make sure it sinks in, because even though we're going to get a little bit complex, I want to make sure that we don't lose sight of the big picture. So, let's see. Nose. That makes an automatic thing. I didn't know that. Let's try this again here. We have our forehead, eyes, nose, mouth. Okay. Eyes, mouth, hair. Okay. We bring in food. I mean, it really is this simple at the end of the day. We bring in the food. The nutrients travel to our GI tract. Then we're going to absorb those nutrients because we've now broken them down, and we have glucose, which is the simplest sugar or carbohydrate, and we have fatty acids, which are the smallest pieces of fat. And we're going to send these food breakdown products to the muscle. But you see, we have to convert these into ATP, because ATP is what actually goes to the muscle to get it to contract. So what we're about to talk about is the process of converting nutrients into ATP. Converting nutrients into ATP. Now, this takes part inside the muscle. So if we have our big old muscle, tendons on the end, we're looking microscopically in that muscle. Because in each muscle cell or muscle fiber, we have the mitochondria. That's this yellow thing. We also have the cytosol. This is just inside of the muscle cell. We are going to convert glucose, or maybe fatty acids, into ATP, because ATP is the usable energy source, which will cause the actin and myosin to slide past each other. So now we're deep in the weeds in chemistry. Okay. So the process of converting, bear with me, of converting glucose into ATP. That's what these steps are. We start with glucose, we go through this process, then we go through this process, and then we go through this process. There are 3 chemical processes. In other words, it's a bunch of chemical reactions. In order to get glucose, so we're inside the muscle cell, in order to get glucose converted to that ATP or usable energy, a bunch of chemical reactions. And we can break those chemical reactions into 3 different series of steps. Creatine phosphate, anaerobic glycolysis, and then aerobic metabolism. So the first step is this, right? Converting glucose into this. Second step is this. And our third and final step is this. Bunch of chemical reactions into 1, 2, 3 little chunks. Okay. What do we do first? Something called the creatine phosphate energy system. Really quickly going to convert glucose into ATP. Even though it's not going to get the big bang for our buck, this is going to give us the most ATP, 36. Here we're only going to get 2 ATP. So it's quick. We're not going to get as many ATP as possible. But if we need quick energy, this first process, creatine phosphate. It is our first chemical reactions. It does not require oxygen. Some of our processes require oxygen, some don't. This first process is what our muscle cells use first, no matter what kind of exercise you're doing. It is anaerobic, does not require any oxygen, so we can do it quickly, and it produces some ATP. For every 1 glucose molecule you put into this system, it yields 2 ATP, which is not very much. Not very much at all. But if we need quick energy, this is all we got. Usually, those 2 ATP are enough to fuel your actin and myosin of your muscles to contract for about 10 seconds of exercise. So if I'm just doing about 10 seconds of exercise, I'm able to use just this first step. Those 2 ATP are enough. You'll see this process is called the creatine phosphate energy system. Let me just peek ahead from, This is called, there's many different ways to call it. You might just hear it called glycolysis. We're going to utilize the creatine phosphate energy system. Excuse me again. The reason why it's called that is because one of the ingredients that we need is creatine phosphate. Everyone has heard of, probably, the creatine supplement. So our body makes its own creatine phosphate. And as part of this first set of chemical reactions to produce ATP really quickly, we utilize our own chemical produced called creatine phosphate. All the rest on that slide is extra. So even though the body creates its own creatine, the idea between a supplement is that even though it creates our own, if I take in more, maybe instead of only generating 2 ATP from that first series of chemical reactions, maybe I can get 3. And if I can generate more energy, I could run that fast for just a little bit longer. So that's the idea behind creatine. We know that creatine is part of this first process. I just got all sorts of crazy, didn't I? We know that creatine is part of this first process. So if I give myself a little more creatine, maybe instead of producing only 2 ATP, I can produce 3. And just that little extra boost, because remember, we're only utilizing this energy system for about 10 seconds. That's enough to lift a heavy weight, run a quick sprint. So even though 1 ATP extra may not sound like a lot, in this type of really high intensity, it could make a difference. Okay, this is all extra. I mean, let me repeat that. Let me be clear. I want you to know that creatine phosphate is part of this first set of chemical reactions. I want you to know that our body makes it. And I want you to have the idea to understand that if we take a supplement, in addition to what our body makes, now we have even more. The idea is that we'd be able to contract and produce a little bit more force because we have that little bit extra ATP. Okay, this is all extra, just giving you the information. We'll talk about this supplement later this semester. This is basically a synthetic form of the creatine phosphate that we already produce. The idea is if I bring in more of this, then I can produce a little bit more energy in this first system. The short answer to does this really work, because many supplements don't. To some degree, yes, it seems that individuals who take creatine phosphate can get a little boost in very high intensity, short duration activities. This is not going to help a soccer player that much because they're exercising for so long. Okay. Now, that was 1. The creatine phosphate was the first part of the chemical reactions in converting glucose into the usable energy form ATP for our muscles. Well, that only was enough ATP for about 10 seconds. Well, what if I'm exercising longer? Well, if I'm exercising longer and I've utilized all the ATP from that first series of chemical reactions, now I've got to do another set of chemical reactions to produce more ATP. This next one is we're going to call anaerobic glycolysis. It is also anaerobic, does not require oxygen, as the name suggests. This can provide enough ATP to give us an additional 20 or 30 seconds of energy for exercise. You can read about how it works. It is a very complex series of chemical reactions. Blah, 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 blah. Blah, 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 blah. We can yield an additional 2 ATP. So this can give us another 20, 30 seconds of energy. Now, before we go on to the third energy system, because remember, the first creatine phosphate gave us about 10 seconds worth of ATP to contract our muscles. This next one gave us another 20, 30 seconds. So we've gone through all these chemical reactions only to produce a total. I'm going to round it up. Of about 1 minute. Sometimes you might see this to 1 minute, 90 seconds. Because it really depends on the person. I'm just giving you ballparks. So all the chemical reactions to produce all that ATP in the first 2 steps only gives us enough energy for about a minute. If we have all the ingredients that we need, if everything is healthy and working well, then we will move into the third, which is going to be aerobic metabolism. And the key, I'm going to go back, but the key is this is aerobic. The first 2 were anaerobic, right? The first 2, anaerobic. We're able to complete these chemical reactions so quickly because they don't need oxygen. But if we're really going to get to the cash cow of ATP, I mean, this first one gave us maybe 2. The second one gave us maybe 2 ATP. If I want to get 34, cash cow, baby. If I want to get that, we're going to need oxygen. So the idea is we're utilizing these first two, and all the while, your respiratory rate increases as you're exercising to breathe in more oxygen, and eventually that breathed in oxygen makes its way down to the muscle cell. Because once we have oxygen, now we can do this third method, which gives us the most ATP. Really cool. Now, there is this thing, and I know everybody's heard of it, called lactic acid, lactate threshold, blah, 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 blah. So, let's just really clarify this. I'm here to clear things up. When we have anaerobic means first and second processes. When we are producing ATP through those, they're both anaerobic, creatine phosphate system and anaerobic glycolysis. When we are performing anaerobic ATP production, we have a natural byproduct called lactic acid. Hey, no biggie. Folks, this is a natural byproduct. We form it naturally anytime we produce ATP anaerobically. Fine, great, fine, we're good. This is only a problem if it builds up. If we are able to move from creatine phosphate energy system to anaerobic glycolysis, if we have oxygen getting there, then we can move on to 3, and there's no lactic acid accumulation. But what if this process is prolonged, meaning we're not able to get to the aerobic respiration? This might happen during prolonged anaerobic exercise. It might be if you're doing something really high intensity and you really stretch it out, 200-meter run. Well, not so much that. You know what a good example is? 400-meter run. That's one full lap. It's like a really long sprint. Try and sprint one lap of the track as hard as you can. You're really pushing the boundaries of what we can burn and produce anaerobically. Or it might be during an endurance event where you've already been able to tap into the aerobic metabolism, but because of fatigue, we backtrack and we start burning, we start producing ATP anaerobically again. The bottom line is, anytime we have prolonged anaerobic, we're not able to get to that aerobic for whatever reason, that means that lactic acid builds up. It's not a problem in small amounts, but when lactic acid builds up, it can turn the blood acidic. Quote unquote, hit the wall maybe. There's actually a lot to talk about with this, but this is the general way to think about it. Maybe you've heard of lactate threshold. You don't need to know this. Lactate threshold is a point at which, so we know that if we did a graph, because we love graphs as scientists, if we did a graph and we said this is let me rephrase this because I want to make it clearer. Yes. Again, this is not going to be on test or quiz. It's just interesting, maybe. It is to me. If the x-axis is high intensity exercise, and this is time in minutes, that's the x-axis. The y-axis is blood lactate levels. Well, as I exercise at a really high intensity for longer and longer and longer, I'm going to start to build up lactate. And remember, it's a natural byproduct. So we're always going to have a little bit of lactate accumulation. This type of slope is what we would expect to see. Everything's okay. We're accumulating a little bit, but our body's also able to get rid of it at the same time, so it's not really building up excessively. But if I push the envelope, if I'm doing that 400-meter run, one full lap, as hard as I possibly can, at some point, all of a sudden there's going to be a steep spike. The lactate threshold is the point at which all of a sudden lactic acid levels start to really increase, and that's the problem. Our body can handle small levels of lactate. We can get rid of it at the same time. But when it increases suddenly, all of a sudden the blood's going to be acidic and it's going to negatively impact performance. Okay. All right. So I want to finish our discussion on this energy process system, and then we'll take a break and we'll do part 2 of the video. So remember, we produced ATP through creatine phosphate, gave us 2 ATP anaerobic. We then produced more ATP through anaerobic metabolism, also anaerobic. And once we have oxygen in the picture, now we can move on to our cash cow aerobic metabolism. Requires oxygen, but it produces the most energy. We have to be exercising for a little bit of time to get here. It's hard to give a specific number because we're all different. But because most of our exercise sessions last longer than a couple of minutes, we do utilize this energy system a lot, which is a good thing because it gives us the most energy. Yeah. Unlike the first 2 phases, this process can produce ATP continuously. Cash cow, baby. For every 1 gram of glucose, a net 36 ATP. Before, we had one glucose leading to 2 ATP. 1 glucose yielding 2 ATP. But once we bring oxygen in, we can bring 36. Know that number, because we have the presence of oxygen. And just so you know, we can have carbs. The first 2, the creatine phosphate and anaerobic glycolysis, is really using carbs. But once we bring in oxygen and we can get to aerobic metabolism, this is when we'll also start to continue burning carbs, but also fat. And as a last resort, protein. Okay. Here's a nice summary. Good job. We can continue before I take a little break here, because this is along the same vein. Most activities, you're utilizing both anaerobic means, which were our creatine phosphate and anaerobic glycolysis, and our aerobic respiration. But of course, as the duration goes up, as we move down this list here, we're getting into longer and longer activities. So as the exercise duration goes up, we're going to begin to utilize more of those aerobic means of producing energy. So putting it all together, before we take a break here, at the onset of exercise, for the first 10 seconds or so, you're utilizing the creatine phosphate system, which is utilizing glucose, which is a simple carb. As we continue to exercise, this was maybe a 10-second exercise. Now we're getting to a 20-second exercise. Now we're going to start to utilize our anaerobic glycolysis. We still utilize the creatine phosphate, but now we're also utilizing anaerobic glycolysis, and we're still utilizing carbs. But if we exercise for even longer, now we're going to be able to get oxygen down to the muscles, And now we can also utilize aerobic, which means that not only can we utilize carbs, but we can also utilize fat. Notice, my friends, this is a continuum not only in this direction, but also in this direction. If I start to fatigue and I can no longer bring in oxygen fast enough, I can no longer do aerobic respiration. Now I'm going to slide back. So it's a continuum going in both ways. Here are some examples. Same slide twice. Okay, last slide before our break. What affects movement? Well, at higher intensity, we're going to stay more at the anaerobic zone. At a longer duration, we're going to move towards the aerobic end. Listen, training can play a role. As you become fitter, you will more quickly get to the cash cow. That's a good thing. Another positive adaptation to training, to exercise training, is that you'll be able to more quickly get to that aerobic metabolism. If you bring in proper fluid, you're going to be able to burn fats sooner. That's a good thing. So if you ingest the proper foods before, during, after, you're going to be less reliant on carbs and more fast to get to the fat. Okay, take a pause. I'll see you for part 2 shortly.